welcome back to my channel. Today we're going to look at a whole topic review for the National 5 topic of metals. Go to my website to download the accompanying worksheet for this lesson. First we'll start with the definition for metallic bonding. Metallic bonding is the electrostatic force of attraction between positive metal ions and delocalized outer electrons. All bonding is an attraction between positive and negative. In the case of a metal, we have positive metal ion cores which are arranged in a lattice. Around these cores, we have their delocalized outer electrons. These electrons are no longer fixed with one atom. They are free to move, and because of this, metals conduct electricity. By reacting metals with oxygen, water, and acid, we can write what we call a reactivity series. Here is the reactivity series. Our most reactive metal is potassium with the symbol K. This is followed by sodium with the symbol Na, and then lithium, Li. These are the alkali metals. We then have the alkali earths of calcium and magnesium, Mg. This is followed by aluminium and zinc. Iron and tin come next, and then lead. The least reactive metals are copper, Cu, mercury, Hg, silver, Ag, and gold, Au. The most reactive metals will react quickly with water. The metals in the middle will react with acid, and the least reactive metals will only react with oxygen, or not at all. Pause the video now and put the metals W, X, Y and Z in order of reactivity from most to least reactive. The most reactive metal will be that which reacts quickly with everything. In this case, that will be W. The least reactive metal will be that which is quite slow to react. For us, this will be X, which is slow with oxygen and water and moderately fast with acid. So far we have W as our most reactive and X as our least reactive. Looking now at Y and Z, we can see that Y reacts quickly with oxygen and water and very quickly with acid, whereas Z only has a moderate reaction with oxygen and water and a fast reaction with acid. Therefore, Y must be our second most reactive metal and Z our third. Let's take a closer look at the metal reactions. If we react a metal with oxygen, we get a metal oxide. For example, if we react sodium with oxygen, we'll get sodium oxide. You need to be able to write these as word equations and balanced equations. So here we have sodium, Na, plus oxygen, remembering that it's diatomic, to give Na2O. You need to use your valency rules to be able to write the formula. In this case, we're going to put a balancing number of 2 in front of the sodium hydroxide to balance the oxygen, and then a 4 in front of the sodium. If we look now at metal and water, we'll produce a metal hydroxide and hydrogen. So here, if we take calcium plus water, we will produce calcium hydroxide and hydrogen. Turning that into a balanced equation, we have Ca plus H2O to give CaOH2, remember in the brackets around the group ion, plus hydrogen, which is H2. So to balance this, our calcium is already balanced. If we put a 2 in front of the water to balance the oxygen, that will then give us 4 hydrogens, which are also balanced on the right hand side. For metal and acid, you will produce a salt and hydrogen. The name of the salt will depend on what acid you use. For hydrochloric acid, your salt will end in chloride. For sulfuric acid, the salt ending will be sulfate. For nitric acid, the salt ending will be nitrate, and for phosphoric acid, the salt ending will be phosphate. For example, if we took aluminium and nitric acid, we would produce aluminium nitrate and hydrogen. To write this as a balanced equation, we would have Al plus HNO3. You need to learn the formulas for the acids to give you Al, NO3, 3, remember in brackets around the group ion, plus H2. For balancing this, it's always useful to get rid of a 3. So we're going to put a 2 in front of the AlNO3, 3. That now gives us 2 aluminium, which we can put on the left-hand side. And we now have 2 times 3, 6 NO3s. So we can put a 6 in front of the HNO3, and that allows us to put a 3 in front of the H2. By reacting metals with acids, soluble salts can be made. If you want to isolate a soluble salt, these are the steps that you need to take. So the first step is to add excess metal. This means that you'll have some metal left at the bottom of your reaction vessel. You then need to filter this off so that you then just have your salt solution and then evaporate. This will give you your salt. Metals are found in rocks called ores. Within the ores, the metals are found in compounds such as oxides or sulfides. They can be extracted from these ores using different methods depending on their reactivity. So the most reactive metals, potassium to aluminium, have to have their metals extracted from the ores using electrolysis. This is a process that uses electricity to split up a compound into its elements. For the elements from zinc to copper, we will heat them with carbon or carbon monoxide. In this process, the carbon and the carbon monoxide will pull off the oxygen or the sulfur from the compound. For the least reactive metals, heat alone will be enough to remove them from the ore if they are joined to anything. During extraction, the metal ions in the compounds are reduced. This means that they gain electrons. For example, if we found a magnesium ore, we would have magnesium ions. To turn this back into magnesium, we have to gain 2 electrons. This process is called reduction. During electrolysis, which is the most high energy method of extracting a metal from an ore, the ionic compound is broken into its elements using electricity. If the compounds are to be identified, we need to use a DC supply. This is direct current. This means that you will find one element formed at each of the electrodes. We're going to draw this as a diagram. So here we have 2 electrodes. This one is the negative electrode, and this one is the positive electrode. These electrodes are dipped into either a solution or a molten ore. So this is our ore here, which will be made of an ionic compound. What we'll find is that at the negative electrode, the positive ions will gain electrons, and at the positive electrode, the negative ions will lose electrons. So at the negative electrode, we'll have reduction, and at the positive electrode, we'll have oxidation. The process of both reduction and oxidation happen at the same time, with electrons being transferred from one to the other. We can remember this using the mnemonic oil rig. Oil rig stands for oxidation is loss of electrons, reduction is gain of electrons. Page 10 in the databook shows reduction ion electron equations. To write an oxidation equation, you simply flip it over. Pause the video now and try to write these ion electron equations. For reduction equations, you just write them as they are in the databook. So for magnesium ions, we would have Mg2 plus 2 electrons to give Mg. For chlorine, we would have Cl2 plus 2 electrons to give 2Cl minus. For a reduction equation, the electrons are always on the left of the arrow because they are being gained. For an oxidation ion electron equation, you just have to flip the equation over. So the reactants become the products and the products become the reactants. So here, for the oxidation of aluminium, we'll have Al will become Al3 plus 3 electrons. And for bromide ions, we'll have 2 Br minus to become Br2 plus 2 electrons. For an oxidation, the electrons are always on the right hand side because they are being lost. Ion electron equations can be combined to show the resulting redox equation, but to do this, the electrons in each equation must be equal. Let's write out two equations. So here we have copper 2 plus ions gaining 2 electrons to become copper. We're also going to have lithium losing an electron to become a lithium ion of 1 plus charge. When using the databook, you'll find that the more reactive metal is always the one which is being oxidized, and the least reactive metal stays as is written in the databook. We can call this the anti-clockwise rule because you're always going to flip over the one which is higher up. To be able to combine these, we need to make sure that we have the same number of electrons in each of the equations. So in the top equation we have 2 electrons, and in the second equation we only have 1. So we're going to cross multiply. So this whole top equation is multiplied by 1, and this whole of the bottom equation is multiplied by 2. So in reality, we're just going to put in a 2 in front of everything on the bottom equation before we combine. We're then going to have all of the reactants on the left. So Cu2 plus 2 electrons plus 2 lithium atoms to become 2 lithium ions, 2 electrons, plus Cu. We're now going to cancel the electrons because they're the same on either side and rewrite out the equation. We have Cu2 plus 2 Li to give 2 Li plus Cu. A final check is that the charges on either side match. So we have 2 plus for the copper and 2 times 1 plus, so 2 plus overall for the lithium on the right hand side. This is the redox equation. Combine the following equations to show the full redox equation. In this first example, we have 2 electrons in the first equation and only 1 in the second. So we're going to multiply the second equation by 2 before combining. So here we would have Mg plus 2Ag plus 2 electrons to give Mg2 plus 2 electrons plus 2Ag. We can now cancel the electrons and rewrite this without them. So we'll have Mg plus 2Ag plus to give Mg2 plus 2Ag. In this example, we have 3 electrons in the first equation and only 2 in the second. So we're going to cross multiply by the number of electrons that we have. So for the first equation, we're going to multiply by 2, and for the second equation, we're going to multiply by 3. So here, we're going to multiply by 2, and for this one, we'll multiply by 3. So writing out the equations in full first, we'll have 2Al to give 2Al3 plus 6 electrons, and we'll have 3Cl2 plus 6 electrons to give 6 Cl minus. We're now going to combine the two equations. We'll have 2Al plus 3Cl2 plus 6 electrons to give 2Al3 plus plus 6 electrons plus 6 chloride ions, and we can now cancel the electrons and rewrite out the redox equation. 2Al plus 3Cl2 to give 2Al3 plus 6Cl minus. Electrochemical cells produce electricity by the reaction of metals. Electrically conducting solutions are called electrolytes. A simple cell consists of an electrolyte and 2 electrodes. So for example, we could have a beaker here, and we'll put in 2 electrodes, so these have to be 2 different metals. And we can join them with a voltmeter. So here is our electrolyte. This could be something like sodium chloride solution. And then we have our electrodes. So this could be 2 metals, for example, copper and zinc. So the electrons will always flow from the metal which is higher in the electrochemical series to the lower metal. The electrochemical series is found on page 10 of the data book. The metal which loses electrons is oxidized, so that's the more reactive metal, and the metal which gains electrons is reduced. This is the least reactive metal. When we do this, it's more efficient to use half cells. This avoids any reactions which might happen between the electrodes and the electrolyte. So when a metal is placed into a solution of a less reactive metal, we can get a displacement reaction happening. So rather than having that happen, we put the metal into a solution of its own ions, and then that way there'll be no reaction. So for example here, if we put in some zinc, and we can put this into a solution of zinc 2 plus ions, and then on the other side, if we put in some copper into a solution of some copper 2 plus ions, the zinc won't react with the zinc ions and the copper won't react with the copper ions. We are going to link the two with some wires and a voltmeter, and then we also need to have something called an ion bridge to complete the solution. So here is our ion bridge. So this is just a piece of paper which is soaked in salt solution. So it's sometimes also called a salt bridge. This just completes the circuit and allows ions to move from one beaker to the other. So the electrons in this case will flow from zinc to copper because zinc is more reactive than copper. And when we do this, that means that the zinc in the electrode here will be oxidized. So we'll have Zn becoming Zn2 plus and 2 electrons. The 2 electrons will move through the wires to the copper electrode, and the zinc ions will end up in the solution. And on the other side, we'll have Cu2 plus 2 electrons to give copper. So in this case, the electrons will go to the electrode. The copper 2 plus ions in the solution will migrate up to the electrode, will pick up 2 electrons and form copper metal on the surface of the electrode. So the zinc electrode will start to get smaller, the copper electrode will start to get bigger. As this happens, the copper 2 plus solution, which will be blue, will start to lose its colour as the copper 2 plus ions are used up, and the counter ions, so something like nitrate or sulfate, will move across the ion bridge to balance any charges. You can set up an electrochemical cell using non-metal solutions, which you'll see on page 10 of the data book, and in this case we would use graphite for the electrodes. Different pairs of metals will produce different voltages, and this can be used to set up an electrochemical series. It's very similar to the reactivity series, with only a few small differences in the most reactive part. The further apart on the electrochemical series that the metals are, then the larger the voltage that is produced will be. Pause the video now and try this question. So here we need to show the direction of electron flow. So the electrons will always flow from more reactive to less reactive metal. If you look at page 10 of your data book, you'll see that aluminium is higher on the electrochemical series than lead. So the electrons will flow from aluminium to lead. That means that we can write out the oxidation and reduction equations. So aluminium is more reactive and therefore will be oxidized. So we'll have aluminium becoming Al3 plus 3 electrons. Whereas the lead will be reduced. So we're going to have Pb2 plus 2 electrons to give Pb. So here we have our oxidation and here we have our reduction. To combine the two, we need to make sure that the electrons are the same. So we're going to multiply the lead equation by 3 and the aluminium equation by 2 before combining. This means we'll have 3 Pb2 plus 6 electrons to give 3 Pb. And on this side, we'll have 2 Al to give 2 Al3 plus 6 electrons. And when we then combine the two, cancelling the electrons as we go this time, we'll have 3 Pb2 plus 2 Al to give 3 Pb plus 2 Al3 plus. That is our overall redox equation. Name a metal that could replace Pb to produce a larger voltage. So here we have aluminium and then the less reactive lead producing a certain voltage. To make the voltage bigger, and we're going to replace the Pb to do it, we need to find something which is less reactive than Pb. So if you have a look, you'll find that the options we have are copper, mercury, silver, and gold. Thank you for watching my video. I hope that you found it helpful. Please remember to subscribe and ring the bell to be notified of new videos. You can also follow me on Instagram at miss.adams.chem and TikTok miss.adams.chem. Bye for now.